My talk is on accelerating parallel verification via complementary property partitioning and strategy exploration. This is joint work with Jason Baumgartner, Robert Kanzelman, Mark Williams, and Kristen Rosier. Going back to basics, the process of model checking takes as input a model M of the system under verification and a property P representing system requirements. The verification engine then checks if the property satisfies the model, and if not, returns a counterexample trace showing the exact execution of the system that violates the property. However, the situation is a lot different for practical verification tasks. Instead of just one property, there are usually multiple properties to be verified against the model M. A more realistic model checking workflow looks like this. The verification engine checks the model against several properties and reports the verification result for all the model property combinations. A typical example is of the highly prevalent verification task of equivalence checking. In equivalence checking, two designs, design A and design B, are proven equivalent by tying their inputs together and checking the equivalence between their outputs. Moreover, proving equivalences between intermediate design points is often critical for the overall scalability of sequential equivalence checking. Every such equivalence between the design nodes is a property, and proving the overall equivalence between the two designs often entails checking thousands or even millions of properties. The goal of our work is to speed up the verification of multiple property test benches by optimizing the orchestration of very large verification tasks. Property grouping helps improve the overall scalability of multiple property checking. The different properties are partitioned into high-affinity groups based on structural similarity measured in terms of cone of influence. The properties in a group are then verified concurrently, and the different groups can be verified in parallel. The verification effort expended for a property in a high-affinity group can be directly reused for verifying other properties in that group. The verification of group properties significantly improves end-to-end verification performance. The verification and performance impact is more pronounced on localization abstraction, for which the size of the abstraction learned is sensitive to structural similarities between properties that are localized concurrently. State-of-the-art grouping algorithms collect cone of influence information as bit vectors for maximum scalability. Given cone of influence representation as bit vectors, the problem of grouping properties reduces to finding properties with similar support bit vectors above a configurable threshold. In principle, we can use classical clustering methods like k-means, k-midoids. However, we avoid them due to the quadratic comparisons required for their usage. To mitigate this quadratic performance slowdown, state-of-the-art algorithms perform a three-level approximate clustering that groups properties incrementally by utilizing static design information. Given a set of properties P0 to P9, each of the properties is initially placed into a singleton group. Level 1 grouping then generates property groups with 100% affinity by merging properties that have identical support bit vectors. However, verification tasks can often tolerate small dissimilarities between properties, which leads us to level 2 grouping that merges properties based on large, strongly connected components in the cone of influence. Level 2 grouping is then followed by level 3 grouping that merges properties based on Hamming distance between the support bit vectors of the properties. Although level 3 does merge based on Hamming distance, it does so by avoiding the pairwise Hamming distance calculations, which can often lead to slowdowns. The groups generated using the high-affinity property grouping procedure have a provable affinity lower bound. The properties in a group can be checked concurrently, or the group can be semantically refined using localization abstraction. It is important to note that higher levels of grouping generate progressively fewer groups, and the different groups can be checked in parallel. The high-affinity property grouping procedure partitions the properties for parallel verification. It is often the case that the number of available parallel compute nodes are known beforehand. State-of-the-art verification tools utilize different strategies for parallel verification of property groups. There is property partitioning, in which given a set of properties, the property partitioning manager distributes the property groups across identical workers running the same verification algorithm. Then there is strategy exploration, in which given a set of properties, the strategy exploration manager distributes all the properties together across different workers, each running a different version or a different algorithm, different strategy or a different algorithm. However, in the typical usage of these parallel strategies, there is significant resource wastage and redundant computation that should be avoided to maximize verification throughput. Instead of thinking about these verification strategies in silo, we optimize complementary property partitioning and strategy exploration in our work. We identify problems with the typical usage of these strategies and propose optimizations to minimize resource wastage and redundant computation across available parallel workers. In parallel verification, the first problem that we try to solve is that of resource underutilization. Given a set of properties P0 to P9, a property grouping algorithm generates property groups G0, G1, and G2 based on structural similarity between the different properties. The property groups are then sent to a partition manager, which then dispatches them to available compute nodes. The different compute nodes can either be threads running on the same computer, processes running on different processors, or a large computing grid. In this example, the three groups are dispatched to 3 out of 5 available nodes. While the 3 nodes that receive a group each start working on verifying the group, the other 2 compute nodes simply idle. Instead, we could have just distributed the 10 properties across the 5 compute nodes, and that way every node would have been utilized. Although this sounds tempting, we do not want to lose out on the benefits of checking high-affinity properties together. This gives us an opportunity to further optimize the property grouping algorithm to ensure all the compute nodes in a parallel verification environment are fully utilized. Starting with all properties in singleton groups, we first check if the number of singleton groups is fewer than the number of available parallel workers. If that is the case, then we can just return all the singleton groups without performing any grouping. However, if we have more groups than the number of available parallel workers, then in that case, we proceed with the different grouping levels. At any particular grouping level, if that particular level generates fewer groups than available workers, we preempt further grouping and we perform rebalancing to ensure all the workers are utilized. Let's have a look at the group rebalancing procedure. First of all, group rebalancing is only called after a certain grouping level generates fewer groups than the number of available parallel workers. It takes as input groups G, that is the set of groups after that particular stopping level, the number of nodes N, that represents the number of available parallel workers, and then the stop level L, at which grouping was preempted. If grouping was preempted at level 1, in that case the rebalancing procedure picks the largest group G from the set of all groups, and then it halves group G into 2 groups, G1 and G2. Since grouping was stopped at level 1, this means all the properties inside the group have 100% affinity. So whenever we pick a group G and break it up into G1 and G2 for level 1, we get 2 groups that have 100% affinity. We keep repeating this loop by picking different groups from our original group set and subdividing them into subgroups until the number of groups that we have generated is more than the number of available parallel workers. If grouping is preempted at any level besides level 1, in that case, we pick the lowest affinity group G from the set of all groups, and then we roll back that group G into 2 smaller subgroups, G1 and G2, such that both groups G1 and G2 have a guaranteed higher or equal affinity than the original group G. We continue doing this for all the different groups until the overall number of groups that we have is higher than the number of available parallel workers. Going back to our example with underutilized compute nodes, in which 2 out of the 5 compute nodes that were available, they were idle. The improved property grouping algorithm with rebalancing now has the ability to roll back groups G1 and G2 to smaller but higher affinity groups. Since now we have 5 groups to verify, the property manager can distribute those 5 groups across the 5 available compute nodes, and then each node works on a separate group. This guarantees that we would have full utilization of available resources. Another common problem which we have in parallel verification is that of idle processes or parallel workers. The problem entails that although some compute nodes are working on difficult properties, the other compute nodes that have finished verifying a particular property group start idling. Going back to our example with 3 groups and 3 compute nodes, each compute node works on an individual group and tries to prove the properties in that group. Now it may happen that groups G0 and G1 were easier than group G2 and can be proved easily. Once they are proved, 2 nodes start idling while the third node continues solving group G2. From the perspective of overall verification, we might be better off by just distributing the remaining properties across the available compute nodes. However, we do not want to preempt the worker solving group G2 as it may be very close to a solution. Our rebalancing procedure enables us to split the unsolved group and dispatch unsolved properties across the idle nodes. It does this while still keeping the benefits of high affinity group verification. These smaller rebalanced groups might be easier to verify compared to the original group G2, which can overall speed up the entire verification process. Now, there are several other common problems that affect parallel verification strategies and why it's not trivial to utilize a parallel verification environment. There is the problem of redundant computation across workers when each worker verifies the same group at the same time. And this can often lead to result races in which one group, as soon as it finishes solving a property, has to preempt the progress of the other group. Our iteration order heuristics combats this problem by allowing a finer grained control on the order of group iteration in individual processes. Then there is the problem of progress inhibition, in which a worker gets stuck on a hard group and several easier groups might follow. Our controlled repetition heuristic enables fast, lossy, and aggressive verification strategies that enable pausing the verification of hard groups, progressing to easier groups, and eventually returning to the hard group. It is important to note that incrementality in the verification engine is essential to fully utilize controlled repetition of property groups. Lastly, there is the problem of time degradation, in which a group cannot be proved even after several repetitions. Now, it might be the case that although the group itself is very hard to prove, the individual subgroups in that group might be easier. Our decomposition heuristic allows us to decompose the hard-to-prove property groups into smaller subgroups by utilizing our rebalancing procedure. We evaluate our proposed techniques in a redundancy removal portfolio. Redundancy removal is a core algorithm for sequential equivalence checking and reduces the composite model by identifying equivalences between intermediate design points. Each equivalence is a property, and typical redundancy removal tasks often have thousands of properties that have to be checked. While the easier equivalence properties are solved using lightweight techniques such as simulation or k-induction, the harder and non-inductive properties are solved exclusively using localization abstraction, for which it is the best known technique. To give you an overview of localization abstraction, localization abstraction is the process to remove irrelevant logic in the cone of influence of a property, that is, the part of the logic not required to prove or falsify a particular property. Property grouping enables concurrent localization of high-affinity properties without risking vastly disjoint cone of influence logic that may be difficult to prove. Given two properties, P1 and P2 in a high-affinity group, localization learns the abstract design information required to prove the two properties. For maximum scalability, a localization engine may optionally choose to semantically partition the high-affinity group based on differences in the cone of influence of the two properties P1 and P2 with respect to the abstract design learned using localization. In this work, we design a 6-process localization portfolio to solve the difficult non-inductive properties that arise in redundancy removal applications by optimizing both strategy exploration as well as property partitioning. Our 6-process portfolio optimizes localization abstraction across different dimensions with varying property grouping levels, whether semantic partitioning is enabled or not, and different combinations of the heuristics that we propose. We utilize two types of localization strategies in our portfolio. The first strategy is fast and lossy, in which we run localization with imposed time limits and resource constraints on how much time and effort we spend performing bounded model checking and how much time we spend in individual SAT queries and whether proof-based abstraction is enabled or not. The other localization strategy is called aggressive strategy, in which we impose no limitations on how we perform localization, but we do have a hook to either enable or disable semantic partitioning. To come up with the best performing combination of localization strategies, we evaluated 36 different single process localization configurations and chose the final set to consist of 6 single process configurations that maximize the number of unique solves per configuration. Our portfolio consists of 3 processes with fast lossy strategies, so that's S1 to S3, and 3 processes running aggressive localization strategies, so that is S4 to S6. The individual strategies in the portfolio differ in terms of grouping levels, whether semantic partitioning is enabled or not, and they use different combinations of our proposed heuristics. To measure the impact of our 6-process localization portfolio on redundancy removal, we compare 4 different localization portfolios derived from our best portfolio. Firstly, there is the base portfolio that does not perform any grouping whatsoever, and all the processes solve properties in the same order. Note that base represents a state-of-the-art localization portfolio with without grouping. The next is base plus G, that extends the base portfolio by adding property grouping and semantic partitioning and solves the parallel verification problems of underutilized and idle resources. The base plus G portfolio represents a state-of-the-art localization portfolio with grouping. Then there is the best minus D portfolio that extends the base plus G portfolio with incremental repetition and iteration order heuristics, and additionally solves the parallel verification problems of redundant computation and progress inhibition. And lastly, there is our best portfolio that adds the decomposition heuristic to the best minus D portfolio, and it additionally solves the parallel verification problem of time degradation. We utilize 3 different benchmark sets in our analysis. Sets B1 and B2, they are difficult SEC benchmarks that differ in how the initial equivalences are established over the intermediate design points. Benchmark set B3 is a selection of benchmarks from the model checking competition. Although these benchmarks are single property benchmarks, we utilize them in our analysis to demonstrate the impact of our techniques for redundancy removal to speed up functional property verification. Our overall evaluation set consists of 632 benchmarks that have properties ranging from a few tens to thousands of properties. Now, coming to our results, the best portfolio is successful in optimally balancing work distribution across parallel processes. The three fast and lossy processes solve almost equal number of properties, and so do the three aggressive processes. Due to the uniform work distribution between fast and lossy processes, the aggressive processes can focus on the hardest properties, while the fast and lossy processes chip away at easier properties. In contrast, the first fast and lossy process in the base plus G portfolio solves considerably more number of properties compared to the other two fast and lossy processes represented in orange, which is indicative of scheduling limitations across parallel processes. The ability to optimally distribute work across the parallel processes enables the best portfolio to offer significant end-to-end verification speedups. In contrast to the base plus G portfolio, which represents a state-of-the-art portfolio with grouping, the best portfolio achieves a median 2.4x speedup, and it successfully solves 18.1% more properties compared to base plus G. In summary, the techniques that we present in our work improve parallel verification of multi-property test benches. Although we show improvement from the perspective of a localization portfolio, the presented techniques are applicable to a wider variety of multi-property verification tasks. We optimize complementary property partitioning and strategy exploration. We also extend property grouping to guarantee full utilization of available parallel resources, and we also propose heuristics that optimize work distribution across the parallel workers. We demonstrate the scalability of our proposed techniques by using them in a state-of-the-art localization portfolio for redundancy removal that achieves significant end-to-end speedups compared to existing techniques for localization and redundancy removal. Thank you.